and we are a collection of mechanical engineering students. The problem we've been working on for the last 2 semesters is how to purify water on the surface of the moon. Space exploration companies would like access to purified water on the surface of the moon for use in electrolysis for making rocket fuel, as well as for consumption for lunar habitation. Space exploration companies are willing to pay a lot of money for this because as it stands right now, it's approximately $1.5 billion to take 1 cubic meter of water to the moon. So there is a huge margin for profit. The solution that we've come up with is to take advantage of the fact that many of the components that we're trying to filter out of the water, so things like ammonia, H2S, methanol, ethylene, and SO2 are lower boiling points than the water that we want to keep. So our solution is going to pass the fluid through a very specific temperature gradient, boil off the components we don't want, leaving us in the end with purified water. The model that we're presenting today is mostly software-based, and the heavy lifting comes from a simulation we put together using Aspen chemical engineering software. On top of that, we have 3D CAD modeling rendering our system, and piping and instrumentation diagram, a logic flow chart, and 3D printed scale model of our design. I'm going to let Hariel take you through the Aspen simulation that we put together.
Thanks. So our team was tasked to design a filter system capable of extracting pure water on the moon. And how do we design that? How do we simulate that? So we decided to go with Aspen. Aspen's a software tool often used by chemical engineers to design and optimize various chemical processes. It enabled us to set certain parameters in our design, such as flow rates, feed composition, operating temperature and pressure, and other things. Our feedstock consists of about 8 different compounds, which enters our surge tank, which separates about 4 of the 8 compounds. The 4 compounds leave the surge tank in a gaseous phase, and the remaining 4 enter the distillation tower in liquid phase. Our distillation tower consists of packed columns, which are made up of stainless steel collar rings. It consists of 6 different stages. The top 3 stages have a smaller diameter than the bottom 3 stages. And 3 of the 4 compounds leave that distillation tower, leaving us with 1 compound, which is water. And our complex chemical process enabled us to extract 99.42% pure water at the end. That, and we'll move on to Jeremiah, who's going to talk about more.
Okay, so since this system is operating on the moon, a lot of thought and consideration had to be put into automating it. So we have a lot of sensors, control valves, and pumps, all feeding off of each other and communicating with each other to optimize the processing of the water. As Hariel said, once the liquid is put into the distillation column, it's really important to have a temperature gradient across this, which is what's used for the separation, boiling off the volatiles and leaving water as the product. In this case, the water settles into the bottom here. The liquid water settles into the bottom. It goes into a reboiler where the steam is put back into maintain a very high temperature at the bottom. In the top, all the gases, these are the unwanted gases, go through a condenser, are cooled, and then put back in here to maintain a cool temperature at the very top. Some product is taken away, and that's how you get our separation. And then the water that is not evaporated in the reboiler is sent through here, tested for purity. If it doesn't reach the purity that we want, then it's sent back around to be reprocessed. When it is at the purity that we want, we can use the heat that's in that to heat the enclosure that this whole system is going to be in. Now I'll pass it to Leo.
Hey, I will introduce the maintenance plan for the for our client. Our client actually is going to send the maintenance personnel to space to do the inspection every 6 months. And the picture shown on the screen briefly shows the schedule and some general tasks that the maintenance staff need to be care with. The plan will not give any specific solution to any problems, but instead, it will provide some general procedure to follow to approach to do the inspection. If some problem has been detected during the inspection, the maintenance personnel, they are responsible for fixing those, since before sending them to space, they must be aware of what is expecting to happen, and they must be the expert in those areas. And next, I will pass to Dustin for mechanical design.
Hi there. I was in charge of one of the only mechanical things that we got to do, so that was good. Since we're building this thing on the moon, we had to use standards that I didn't know about, so we chose to use NASA's standards for all of the mechanical pressure vessels and the fittings used. So we're going to start with the stuff that's custom to us. We had to, from the Aspen model, we had to manufacture and design, or well, we didn't manufacture it, but we had to design the surge tank, the column, and then the reboiler and the condenser. So when doing these, when designing these, we had to use 316L stainless steel. Not so much, we didn't need too much for pressure because the peak pressure we have is about 220 kPa. So it's not, we didn't have to worry about that, but we had to worry a lot more about the corrosive material that's going to go through them. We made the column out of 6 different components because we had 6 different stages. So as you could tell, it might be pretty hard to get it up into that stack unless those pieces could come apart. So this is something that could be assembled or disassembled in the enclosure. As well as all of the components that we had to design, we had to pick components that were for off the shelf. So we decided to go with a sealless type pump so that we could maybe hope that it would be more it'd be better for long-term use so that we wouldn't have any kind of seals that would go bad. All the on-the-shelf parts like solenoids and the pumps and the temperature sensors and level sensors, all those were picked for the environment with the heat and corrosiveness. Again, we have our rad as well. We can go through a little bit better of the design portion a little later. I did want to start now with sending this around. This is our CAD model, just in 3D printed form. I'm sorry if I can't see it with the camera, but basically what we're planning on doing is making the enclosure out of aluminum and then burying it in regolith, so the dirt that's on the moon. So we're hoping that that would help from shielding it from sun's rays, as well as maybe keep some of the heat in at night. So yeah, from that, we're going to give it off to Jordan. Sorry.
So just to summarize, we've figured out a solution for purifying water on the moon. Our model is software-based and combines simulation, piping and instrumentation diagram, 3D CAD modeling, maintenance schedule, and a 3D printed scale model. Our solution will produce up to 26,000 kilograms of pure water per month and has the ability to save the undesired constituents for future use if that's deemed necessary. At this point, this is the end of our presentation. Thank you very much, and we'll open it up for questions.